The aim of this presentation is to introduce percentage uncertainties as a principle and how to tactically reduce the percentage uncertainty in particular measurements. Let's take an example task then. So the example task is to make a solution containing 100 grams of sugar per 250 centimetres cubed of water. The concentration, therefore, of that solution is represented as follows. So we're just going to use the units of grams per cubic centimetre in this example, grams per centimetre cubed down here. So this is 100 grams of sugar divided by 250 centimetres cubed of water or of solution volume to give us a concentration of 0.400 grams for every centimetre cubed of that solution. So how on earth can I go about making this? Well, at the moment with the COVID-19 lockdown, I'm a bit stuck because I can't get into the lab. So let's see what apparatus I can find at home to do this job. So I've managed to find in my cupboard this measuring jug which I could use to measure out the volume of water. So here I've got a measurement of 250 centimetres cubed of water. But on this jug there's an analogue scale and the division above that is 300 centimetres cubed and the division below that is 200 centimetres cubed. Now, no matter how carefully I try to work out that volume or measure out that volume, which is 250, in actual fact, there's a limited precision to this piece of apparatus. And because of that limited precision, we have to have some sort of a way of communicating the potential uncertainty in that value. And the convention to use for an analogue instrument like this is we take half a division above and half a division below the measured value. And we use that as the effective range. So half a division above, half a division below, this is the range. Now this division above, because the overall difference in that full division is 50 centimetres cubed, half a division is plus 25 centimetres cubed, and half a division below is minus 25 centimetres cubed. So we would quote this value as being 250 plus and minus 25 centimetres cubed. Now, that's great because it gives us a range and we know that our measured value should lie somewhere between that range, particularly if we've used this apparatus carefully and skillfully. But what limits that information as being useful is the fact that we can only then deal with measurements in centimetres cubed, whereas in our concentration measurement, it would be useful to be able to combine this with the uncertainty in the mass in order to get an overall uncertainty. So that's why we use percentage uncertainty. It allows us to combine different uncertainties measured by different pieces of apparatus in order to get an overall uncertainty in a particular calculated value. So in this example, the absolute uncertainty is 25 centimetres cubed. The value measured was 250 centimetres cubed. Times that by 100, and that produces a 10% uncertainty in the measuring jug value. Now let's consider the mass of the solid being measured. Now in this case, we're using a digital top pan balance. And because this is a digital balance with electronic logic, which works on a yes-no principle, we don't use the half division rule in this case. In this case, we use plus and minus one full division. In other words, we take the smallest measurement that this balance can do, and the overall absolute uncertainty is given as plus and minus that value. So in this example, it's plus and minus 1 gram on this balance. So here's a bowl of sugar, and the bowl and the sugar have a particular mass. So the mass of the bowl and the sugar is equal to 300 grams on the scale, but remember it's 300 plus and minus 1 gram because the limited precision of the instrument. I can then pour that sugar into something else, say a pan, and record the mass of this. So this is the mass of the bowl plus any residue. Now what that means is we have an accurate measurement of the residue left over in this bowl, or in fact we've got an accurate way of calculating exactly what mass of that sugar we transfer to something else. So this is the weighing by difference technique, and the mass of the bowl and residue is 201 plus or minus 1 gram. So consider the mass of sugar that's been transferred to this pan, the mass transferred, and this was weighed by difference, so that was weighing by difference method. So we need to take a difference between two measurements. That was the 300 plus and minus 1 gram for the bowl with the sugar in it, and subtract from that 201 plus or minus 1 gram for the bowl with the residue in it. So that gives us an overall value of 99 plus or minus 2 grams. So 99 is the mass transferred, but there's a plus and minus 2 gram absolute uncertainty. So the percentage uncertainty in that measurement is equal to, let me just edit that text, I don't know what's going on with this screen just now, but we'll keep battling, equals plus or minus 2 divided by the 99 and times that by 100, which is essentially 2% uncertainty. Now we've got some uncertainties and some absolute values for each of these. So the volume that we measured, remember, was 250 plus or minus 25 centimetres cubed, and that was a 10% uncertainty in that measurement. Here the mass of sugar transferred was 99 plus or minus 2 grams, which is a 2% uncertainty. So if we wish to calculate the total percentage uncertainty, we can use the sum of those individual uncertainties because we've used those two measurements together to make a different calculation. So the total percentage uncertainty here is the 10 plus the 2% is a 12% uncertainty. Now if we finish this calculation off, it would be good to work out the actual concentration. So the actual concentration of the solution that we make up by adding those substances together, the actual concentration is going to be not 100 grams this time, but 99 grams as our actual mass. Divide through by 250, and that to 2 sig figs, because this is to 2 sig figs here, will give us a 0.40 grams per centimetre cubed concentration. But remember that there's a 12% uncertainty in that. And so if we work out what 12% of 0.40 is, 12% of 0.40 is 0.05. So our actual concentration, including the uncertainty, is 0.40 plus and minus 0.05 grams per centimetre cubed, which, considering I've used my kitchen apparatus and not lab apparatus, is not bad considering our target concentration was 0.400 grams per centimetre cubed. I certainly wouldn't be particularly happy with that in the lab, mind you, so perhaps now we could start to consider how we could go about minimising these percentage uncertainties. So how could this percentage uncertainty be reduced? First of all, let's do it using only the apparatus available in the kitchen. Well, if we imagine this balance, the percentage uncertainty, remember, is the absolute uncertainty divided by whichever value we've chosen to use. Now, the absolute uncertainty is fixed for a fixed piece of apparatus, so we can't change this. This bit here is fixed. So the only way we could reduce that percentage uncertainty using the same balance is to change the value. And here we could use a larger mass of the sugar. And if we used a larger mass of the sugar, then that would reduce the percentage uncertainty in that measurement. Similarly, if we stick with the same measuring jug, we cannot change this because this is fixed for that piece of apparatus. But we could choose to use a larger volume. And so if we scaled up the whole experiment, this will go up to, this has a capacity of half a litre, so this has got a maximum of 500 centimetres cubed. So if we doubled the volume and doubled the mass of the sugar involved, we could keep the same final concentration but reduce the percentage uncertainty. So that's one method of reducing percentage uncertainties in the lab as well, by just scaling everything up. So the same absolute uncertainty applies, but that's against a larger measured value, so as a percentage it decreases. An interesting other way of changing the percentage uncertainty, I wonder if you'd thought of this one, would be to forget about using the measuring jug at all to measure the volume and instead weigh out the water. So weighing out the water, because the percentage uncertainty in the balance was much lower than the percentage uncertainty in the measuring jug, actually weighing out the water, given that 1 gram of water, 1.00 grams, is 1.00 centimetres cubed of water, we could use masses instead of volumes to do this. And interestingly, I just was having a play with this, and I took the water from that measuring jug, poured it out, and measured the before and afters. So our actual volume that I have measured using that measuring jug was, if you look at this, 883 plus and minus 1 minus 614 plus and minus 1. Which is actually 269 centimetres cubed. 269 plus and minus 2 centimetres cubed transferred, which is quite a bit different from the 250 that I thought I'd measured, but is still within the range of the uncertainty of that apparatus, so that's quite interesting. Another way to reduce the percentage uncertainty is to use apparatus that's a little bit more precise, so has got a lower absolute uncertainty in the first place. So here we've got, for instance, a volumetric flask that we tend to use in the lab when making up these standard solutions. That's got an absolute uncertainty of plus and minus 0.3 centimetres cubed, which is more like a 0.12% error. So 0.12% uncertainty or thereabouts. So that's quite substantially different from the 10% that we had with the measuring jug earlier. And similarly, by transferring two measurements using a top hand balance, which records to 2 dp here, the plus and minus 0.02 grams out of the 100 grams being measured is of course a 0.02% uncertainty in that particular measurement, and so that would be a big improvement as well. So to improve the precision of a particular experiment, using more precise apparatus is certainly a good way to go if you have it to hand. So by switching from non-specialist apparatus to these two pieces of apparatus, the total percentage uncertainty using the same measurements as used in the kitchen experiment reduces from 12% to 0.14%, which of course is why we use standard lab apparatus to do things properly in the lab. Okay, that was an introduction then to percentage uncertainties and how to work with them. This is an introduction so that you can then get on with some of the examples from the workbook that you've been given. So try to apply these ideas to some worked examples and perhaps use this video for reference in the future when you're doing some of these things live in the lab yourselves.